Welcome to our machine learning lecture series here. My name is Ben Bischel and this is the third part in our chapter on multi-target prediction. So here we will study the first bunch of hopefully not too complicated algorithms for handling multi-target learning problems. So in the first class of methods, that's I guess one of the most naive and simplest forms of modeling you can envision for multi-target learning. So you'll discuss the independent modeling of each individual target column. We'll talk about mean regularization, we'll talk about stacking, and we'll talk about weight sharing in deep learning. Okay, so as I've already said, it's not that difficult. Let me actually move out a little bit of the way so you can see, I guess, also the slide numbers here. So the most naive approach of handling a multi-target learning problem is just fitting an individual machine learning model to each of the target columns. So as you can see here, you can see these guys. Just forget about all of the rest to just model everything individually. If you have a multi-label learning problem, and that multi-label learning problem you could encode with a bunch of 0, 1 columns, where each one per column would encode that label is actually there for this multi-label example. This independent modeling with binary classifiers, so one binary classifier per column, would be called, I guess maybe somewhat confusingly, binary relevance learning. I guess the name is partially intuitive. I guess it wouldn't have been really that much necessarily, but this is how this is usually called in the literature. Advantages are pretty obvious for this approach, right? It's super easy to implement, and the real advantage is there's a huge wealth of methods available. You can even use different machine learning techniques per column. You can even run a little bit of model selection or a little bit of AutoML or hyperparameter optimization to model as each individual column as good as possible. And it's also quite clear how much we pay for that in terms of computational efficiency. So instead of learning one column, we now have to learn, I think our usual letter for that was L. So L time is expensive, right? As L time is expensive as how much time we would spend for, how much time we would be okay with investing for modeling a binary classification problem of the same size. Now, it's also pretty obvious what the downside of that thing is. So we can't really exploit any form of correlations between the targets, and I guess that is what multi-target learning is about. So this is more or less kind of a baseline technique. Nonetheless, in some benchmarks or in some applications, not that easy to beat, as you will see later on when we present a few results. So there's also a way of dealing with independent models through a linear, kind of an integrated linear modeling approach. So assume we would use one linear model per column. So maybe there's also some feature extraction going on, and this feature extraction would be represented here by our basis function vector phi. So that's just some form of feature extraction on our feature vector x. And then we model that with a linear form per target column. So we have these functions fk, which are theta transposed, theta k transposed, times our extracted feature vector, and we have one of these linear models per column. So far, so simple. Now we can use this, so we will usually use this if we have a huge number of targets. So in some applications you might have, I don't know, thousands or 10,000s or 100,000s of targets, and you would have an integrated approach which scales fairly well to this super huge number of targets. And we can now optimize this thing here jointly. So if you look at the first part of this, this takes our matrix Y. So Y would be our matrix of, so this would be a n times, I guess, L matrix of outputs. So we would have obviously n rows because we have n observations, but we now have also L columns, so it's not a single vector. It's a matrix because it's multi-target prediction, right? And here on the inside, we have phi. So this would be our matrix of extracted feature vectors. So here you would do a feature extraction for the first example, for the second, and until the nth. So I guess this is our regular design matrix. And phi theta. So this capital theta is simply a matrix where we have organized all of our theta parameter vectors of all of these linear models, one per column, in the columns of that capital. So this is actually just a very fancy way of kind of in parallel modeling all of these columns in matrix notation. So if you would compute capital phi times capital theta, you just get a matrix y hat of also this dimensions here, n times l. You now compare this with your matrix, with your target matrix capital Y, and then you compute the Frobenius norm on this, which is just a very, very fancy way of saying we are computing the sum of the SSEs for all of the columns individually. So if you look at the formula here, you should immediately see this, right? So this Frobenius norm now acts on this difference matrix, where we compute the difference between y and y hat. So for each cell entry, that's a residual for a certain observation, for a certain target. And now you square all of these residuals, and I guess maybe you could say we square them first for a given column of all of the rows, and that's the SSE for that target, and then we do that for the second target and for the third and so on, and at the end we sum it all up, so at the end we kind of get that global SSE. Okay, and because we want to have that usually regularized to avoid overfitting, we now put a rich term on top of that, so an L2 penalty term. I guess we're actually doing that L times, so we might even have, if we are unlucky, L hyperparameters here, so 1 for each 2 norm of our theta m guys. And this can still be fitted quite efficiently, as you know, for these rich regression models. Also for individual columns, we can even find an analytical solution, can handle that quite well, and this scales also to quite large amounts of data in N, in P, and also now in L, because we now, as I said, this would usually be applied to pretty huge scale multi-target learning problems with large Ls. So usually, how would that look like in a paper? So very often these independent models, right, these baseline models, they would be compared to some, I don't know, more interesting approaches here. So this blue guy would be this independent model, right? We would run an evaluation scheme as we've discussed before, and then compare that to more interesting techniques. And the idea is to get a better result out of this by exploiting dependency correlation among these targets. And we'll now go through a bunch of simple techniques how this could be done. So one really simple technique would be enforcing similarity in deep learning. So we would just use a common architecture, a common deep architecture that we would like for our task, and that would make sense for all of these targets. And then we would simply have in a final layer of m output nodes, so I guess before we call that L, sorry, with weight sharing now among the targets, and you just fit that under one of these joint losses for multi-target prediction that we introduced before. Maybe something, if this would all be regression, this sum of SSE over all of the columns as we have done in this multi-target linear regression problem. A second technique would be a mean regularization. This is also pretty simple to explain, and I guess we could do that for different models, but here this is explained again for this multi-target linear regression setup. So before, again, not before. So as the first component here, we have again this joint SSE over all of the columns, as we have discussed before. And here, as the second term, now we have a specific penalty construction, which works like that. So the idea is that models for similar targets should probably behave similarly. So in that case, the parameters should be similar. So this idea we are now introducing into our model by saying, hey, how about if we now bias parameter vectors towards a common mean vector? So if you look at this, what you now do is you compute the mean vector over all of the parameter vectors here, and you compute also now for each theta m the difference to this mean vector, and you measure that again by the L2 norm. So you would really need some kind of hard evidence in the data that a difference from that mean is warranted because it gives you a huge reduction here in risk. Only in that case, this guy here would be considerably different from this guy. Okay? Pretty versatile, model agnostic, general meta technique is stacking. So stacking has actually originally been introduced as a general ensemble learning technique where you would like to create a heterogeneous ensemble across a pretty diverse bunch of different model classes. So the idea would be I have a certain data set, I run, I don't know, a decision tree, a random forest, a boosting model, I don't know, a linear model, a neural network on this one data set. And I would now like to have a principled way of combining these models. Maybe even just through a weighted sum, but it's somewhat unclear how to do this best, right? Well, actually, turns out it might not be so unclear, because what we could simply do is we could collect all of the predictions of our, we call that, of our first level ML model. So this would be all the models that we have fitted on our data set, potentially have cross-validated them, and now collected a cross-validated prediction vector for all of these models. And now we just put a second ML model on top of that. So we are asking, how can we optimally combine or transform these prediction scores to end up with a loss minimal common prediction. And this is what we would call a level 2 model. So this level 2 model would combine these predictions. Okay, this is how stacking would work as a general ensembling technique to combine heterogeneous ensembles. The whole idea also, or I guess the whole insight behind that is that if you have these models of pretty different strengths, pretty different predictive performances, it might not make sense to just combine them straightforwardly with a, I don't know, with a mean, right? Or just averaging them, because some of these models might work better, they might have a lower error, others might have a higher error. Of course, you can now take these performances and try to transform them through some, I don't know, heuristics into weights, but I guess framing that, writing that down again as a machine learning problem, might be the more principled approach to end up with a loss minimal solution. And if you really want to have a weighted combination of these models, why not just combine them at level 2 with the linear model under, I don't know, a loss function of your liking, maybe L2 loss. You can also ask for a sparse ensemble and then use a linear model with a lasso penalty, so with an L1 penalty to make that sparse, and then you get a sparse linear combination. Now, anyway, how can we use that for multi-target prediction? Well, pretty similarly. So first of all, we would use our naive approach. So we would model all of our targets individually, okay? And our remaining task now is to exploit the correlation or dependence structure between these independent columns, and we do that by now using a level 2 model, which is now really supposed to model its associated column and target, but it does that by combining all of these guys here from level 1. Okay, so these guys here on level 1, they are fitted independently, and now G1, which would model the first target, is allowed to combine all of these estimated outputs, which have been estimated independently, into kind of a joint prediction for the first column. So I guess this model will rely pretty heavily on this. So G1 will rely pretty heavily on F1 because F1 was already tasked with learning the first target, but it can use and refer to these other guys here, to these other level 1 models for the other columns to exploit this dependency and kind of improve its prediction for the first column. And again, this is quite easy to implement. It's not much harder than just doing this, this independent column modeling. This has been shown to work quite well. Again, also, I guess from a software engineering perspective, or from a toolkit perspective, you now have the freedom of using basically every model class and also maybe some hyperparameter optimization techniques of your liking. It's also pretty clear that this will not scale that well if the number of targets is hugely large. And you can again use regularization in your level 2 models to avoid overfitting or to kind of enforce similar parameters for different targets, or you can also make that sparse if you want to. All of that's possible. And for all of these techniques also, we have given you a bunch of references here at the bottom of the slide. So if you're interested in learning more about this, so here we'll just do a very, very kind of rough summary. So let's now maybe end with looking at hopefully somewhat realistic benchmark. So this is taken from a paper a couple of years down the line where we implemented quite a few of these simple multi-target prediction techniques, I think mainly for multi-label classification into an R package, and we also benchmark this. So this is a bunch of quite common multi-label benchmark sets, and this is kind of an extract here of the benchmark results from that paper. So I didn't copy everything from the paper because quite a few stuff was in there, which is, I guess, I'm not sure whether it's much more complex than what we covered here, but I mainly wanted to compare two very simple techniques. So the first one is this baseline binary relevance modeling, where we just take independent models, and because this usually works quite well as a model in machine learning overall, but also in binary classification, we took a random forest. So we model each column individually with a random forest, and then we computed the F1 score decomposed over targets. So what you can see here, these cell entries are basically the F1 score when you compute the F1 for each individual column and then average that. Maybe this is something I should have discussed a little bit also before. What you have to watch out for, especially in these multi-label / binary relevance learning problems, is that very often you have, if you look at these binary columns, one per whether a label is present or not, these columns here, they look like that, but they will usually be pretty heavily skewed in terms of having a lot of zeros, right? Because for many observations, a certain label will not be present. Well, it doesn't always have to be the case, but it's quite likely that these will be quite imbalanced. So it might be interesting to consider a learning algorithm that can handle these imbalanced problems a bit better, or to maybe use a performance metric that takes this into account. And we didn't really do anything here in kind of on the modeling level. Just took the random forest out of the box, but at the very least we try to measure this properly by using the F1 score, this kind of average F1 score over columns in evaluation. And the second model that was able to exploit dependencies between columns, so in a certain sense, a true multi-target prediction model, was a stacking model where we used a random forest. I actually can't remember this now. We definitely used a random forest again for the level 1, and I'm not sure whether we use it on level 2 as well, or whether we combined with a linear model. Can't remember, one of the two. And we can now look at the difference here on these individual benchmark sets. And what you can see is, I would say, quite a typical result. So this stacking approach here, which potentially can exploit these dependencies between columns, it does fare a bit better than the quite naive binary relevance approach, but the differences are not super large. So I don't know, here you have something like about a 2% or 0.02 difference in F1. I'm not sure whether we can find much larger differences, not really. So it's about 0.02, 0.01 points of difference. I guess I could even now talk about whether these differences are significant, run a statistical test for that. So there is some gain we get from these models, but just like modeling individually is usually already a pretty strong baseline. So this concludes the session here. Goodbye, and see you in the next pass on a bit more advanced algorithms for multi-target prediction.